All right, let's walk through what we call a two-component process. This is a very traditional chemical engineering style of problem. So we're going to take a liquid stream that's about 60% ethane and about 40% N-butene, and we're going to heat it at from 150 Kelvin to 200 at a specific pressure. And what we want to do is we want to calculate the heat input that's required per kilomole of the mixture, neglecting potential and kinetic energy changes using what we call tabulated enthalpy data for the two components, and assuming that the mixture component enthalpies are those of the pure species. So, tabulated enthalpy data is sometimes, depending on the semester, we have you look up. Sometimes we just give it to you depending on where we're at in the semester. So for this type of problem, we're going to draw a flow diagram, and then we're going to give you the tabulated enthalpy data so that you can see kind of what it looks like. And all that means when we say tabulated enthalpy data is that we can look for a specific temperature and a specific pressure and a specific species and go and find what the specific enthalpy is for those components. So I've done that for you, but we can do that by looking up things in a table if we need to. So first, let's write out what's going on in the system. So we have a system and there's a certain flow rate coming into the system and we've got specific components coming out. So we're going to assume that we have 1 kilomole per second coming on into the system, right? That's our basis of calculation here. That's what we're told in the problem. And because something's coming in and something's coming out, this is not a system where we necessarily have any reactions. We're just heating things up in the system. So our flow rate in is going to be the same as our flow rate out because we're not necessarily accumulating anything in the system and we're not performing chemical reactions. What that means is that the components coming out are also going to be the same. We're going to have about 60% ethane and about 40% N-butane coming out as coming in. But we're adding heat to the system, so energy is definitely changing, even if the number of moles are not. So what you're going to see over on the right side of my page now is you're going to see here's the two different components in the system, and you're going to see these are tabulated at specific enthalpy values in terms of kilojoules per kilomole. So what you're going to see is these would be the values that you would look up in a table. So what you would do in the table is you would look up the pressure, which is 1 megapascal right here. And then you would go to 150 Kelvin and you would look up what is the specific enthalpy of that component at that specific temperature. So that's what these values are, and that's where they come from. So because of where we've gotten to in this semester, I'm going to be giving you these values if you need them on exams. But just be aware that as you move on to thermodynamics or other classes, you might have to look up these values, and there's a way to do that. Okay? The other thing is that we're given the fact that we have no potential energy change and no kinetic energy change, and we're trying to find Q in the system. And let's make a change here. Our basis of calculation is that 1 kilomole per second. I had kilograms written. So let's make sure we're in the right units. So first thing that we want to do is we want to write and simplify the open system energy balance. Now, if we're looking at the boiler kind of as our system, we don't necessarily have changes in what's flowing in the system, but we have a certain mass that's crossing the system. And so that's going to be important because mass is crossing the boundary of that boiler. So for us, that's going to tell us that it's an open energy balance. Okay, the other way, right, that you remember that this is an open energy balance is the fact that we're now talking about enthalpy. Whenever we talk about enthalpy, it must be an open system. Okay, so let's write out our balance. So Q plus shaft work is the change in enthalpy plus the change in kinetic and the change in potential. Let me just adjust my lighting so you can see what's going on. There we go. That's a little better. That way you can see what I've canceled. So we're going to cancel out a work term because there's no indication in the system that there's motors or shafts or anything doing any kind of work. And we know that we have no kinetic and no potential in the system. So what that's going to tell us is we simplify down to a really easy equation where we say, well, the heat that's flowing in the system is just the change in enthalpy, which is good because we have enthalpy values and we can move on from there and just get that Q value. So the key thing that's going to be important here is remembering that when we do enthalpy, it's out minus in, the sum of everything going out and the sum of everything coming in and the difference between the two. Now remember, enthalpy, specific enthalpy, right, can be in terms of moles or mass. And the tabulated values that I gave you are kilojoules per kilomole, and everything in our problem is in terms of moles. So that's important here because you're going to want to remember that you're multiplying n dot times h hat. You don't want to have an m dot here and try and convert with molecular weight. That's going to make your life way too hard. So remember that your enthalpy, right, could be, your specific enthalpy could be in terms of moles or mass. So let's move on down. We have all of the information that we need to find Q, so let's go and find it. So one thing that's going to be important about this particular problem is that we sum everything out and then we sum everything into the system. So when we're looking at what's coming out, there are two species coming out that have enthalpies associated with them, right? So C2H6 has an enthalpy coming out of 1,174. But if we look at what's flowing in terms of enthalpy, the 1 kilomole per second is the total molar flow. So that means we need to multiply it by the fraction that's related just to the C2H6 to make sure that this whole value is just related to C2H6 out. The same thing needs to happen for the C4H10 in order to make sure that we are accounting for what's coming in. So we want to take the 1 kilomole per second total, multiply by the fraction that's related to this specific species, and then go find that enthalpy value that's related to that species. Now, how do you know which enthalpy values to put in? Well, we need to look at temperature. Temperature coming in is 150 K. Temperature coming out is 200 K. So what that's telling us is that we need to make sure that we're grabbing the out values because the out is what comes first, right? Out minus in. So the same thing is happening over here. I've just dropped the 1 because there is a 1 kilomole. And so we need to make sure that we take, this is the C2H6 fraction coming out and the enthalpy coming out, this is in over here. And then we have the fraction in and the specific enthalpy coming in the system. So that will give us a Q value of 4,464 kilojoules per second. And just double check your units here as you do this. It's a flow of heat, so we want it per second. The other thing that you want to watch out for in this specific problem is things coming out, you have to watch out for both species. So far, we've only done problems with one species coming out. So you need to remember when you do this formula right here, it looks super, super simple, but it is the change. So it's everything coming out minus everything coming in. That's what that summation sign means. So that's going to be your two-component example. Not too hefty in terms of the different steps, but knowing how to use these steps is what's going to be critical moving forward in our energy balances.